Welcome everybody to another video in our series on forecasting. I'm Stephan Kolassa. I'm a data science expert at SAP Switzerland. I'm also affiliated with the Lancaster University Center for Marketing Analytics and Forecasting. And today we'll talk about forecast selection and combination. So the question that we're going to talk about today is how to deal with multiple forecasts. So multiple forecasts in the sense of having multiple forecasts, multiple data, multiple possible forecasts for the same point in time in the future. So one forecast could be, and these could come from different model classes, like we might have an ARIMA forecast, we might have an exponential smoothing forecast, we might have boosting, deep learning, what have you. We might have judgmental forecasts, so forecasts that just come in from humans that threw something into the pot. How do we deal with all of these? Or even we might have different models within a class. So we might have ARIMA forecasts, but within ARIMA there is a plethora, actually infinitely many different forecasts. Like we might have an ARIMA 101 versus an ARIMA 200, so your experts can explain to you all the details about how these differ at excruciating detail. We might have seasonal versus non-seasonal exponential smoothing, or any of the other of the rest of the zoo of exponential smoothing methods. And of course, in boosting or deep learning, we might have different parameterizations or different hyperparameters or what have you. So we might have lots of different forecasts all for the same point in time. So picture a room full of forecasters and everybody is screaming their favorite number at you for one point in time in the future. How do you deal with those? How do we get a single forecast to act on? So here's a little time series which I took from the M3 forecasting competition, and I just calculated 3 different forecasts, and I didn't really pick any ones that made a lot of sense, but here's one benchmark that you should always keep in mind, which is the historical mean, which is surprisingly often very, very effective. Just take historical data, take the average of those and forecast that one out. Of course, that's a flat line. And people often complain, flat lines can't be sophisticated. Well, actually, often enough they are. It's a question of knowing when the flat line is best. So you could also call the historical mean forecast an ARIMA 000 forecast. That sounds much more sophisticated, but it's the exact same thing. You could also have something like an ARIMA 303 seasonal with seasonal model 100. That sounds much more sophisticated. The forecast also looks more sophisticated because it wiggles up and down. That doesn't mean it's going to be more accurate. Or finally, a third contender would be an exponential smoothing forecast which has multiplicative error, no trend, and additive seasonality. And I just pulled that out of a hat. So now we have 3 different candidates. How do we deal with these? We want one forecast to act upon. There's essentially 2 ways of going about this. There is forecast selection, forecast combination. Let's look at these in turn. Forecast selection is, well, just what it says on the tin. It's selecting. It's a question of selecting one of these 3 forecasts. We're going to go with one of these 3, and later on, combination. Probably not going to surprise you by telling you that combination means we combine these. Let's stick with selection for now. I'm just going to select one of these. But how do we do that? We have 3 different ways, 3 different forecasts here. How do we select? 3 different ways I'm going to present today. One is going by in-sample fit. One is going by information criteria. One is going by holdout performance. Let's look at these in turn. Selection by in-sample fit. So if we have a time series and we have our forecasts, then most statistical methods and most machine learning methods too will give you an in-sample fit. So they will say what the model thinks would have been the average demand or whatever you're forecasting in sample, on top of which there is also some unavoidable noise, because a time series always consists of the systematic component that we're trying to forecast and something that we can't capture, and we call that noise. And what we have here, the red lines in our little pictures here, are the in-sample fits. That's a systematic component in the training sample. Of course, now we might want to say, well, let's just pick the one that worked best in sample, because that obviously understood the data in sample, in the training sample best, because it's fitting best. And then, of course, you'd say this flat line at the very top doesn't do a very good job because there is a lot of wiggling that the flat line doesn't capture, and the seasonal methods are much better, so we should be picking one of those and just use your favorite error measure and pick the one that scores lowest on that error measure. It's actually very simple. The problem is that you should not do this. You should really not do this. Let me repeat, you should not do this. Why? The problem is once you have a given model, you can always make it more complicated by adding components, by adding autoregressive orders. It can go from AR1 to AR2. You can, in an exponential smoothing method, you can say, okay, I have a method with no error, with no trend, add a trend component. Making a model more complicated will always improve the in-sample fit, simply because the model has more leeway, it has more way of turning of tweezing, swing things around and fitting in here and fitting in there. It's more flexible, and that means you can adapt better to the in-sample time series. The problem is that it will at some point in time start fitting the noise. It will start thinking that it understands stuff that is simply noise, that is simply unforecastable random variation. And the problem is you will not know, because in sample, making a model more and more complicated will look like it's doing a better and better job. And at some point in time, out of sample, it's going to get worse. So do not do that. Do not rely on in-sample fit as a forecast selection method. This is overfitting. Don't do that. All right, happily enough, there's other methods. One alternative is information criteria. So we again have the in-sample fits here, but we also have cryptical abbreviations like the AIC and the BIC. If you have a statistical forecasting method like the ARIMA or exponential smoothing, these will also give you information criteria. So these are KPIs, key performance indicators, of a statistical model applied to data. There's different flavors here. There's Akaikis information criterion, the Bayesian or Schwartz information criterion. That's the AIC and BIC that we have in here. And those are essentially the in-sample errors that we just talked about, but they're penalized by the complexity of the model. So you don't just look at the in-sample accuracy or in-sample model fit, but you penalize this number by the complexity. So at some point in time, this complexity penalty outweighs the in-sample fit. And so what you're doing then is you select the forecast with the lowest information criterion. The absolute numbers don't really make a lot of difference. They differ by implementation, but it's just if you have multiple forecasts, just select the one with the lowest information criterion. You can deal with AIC, you can use BIC. It doesn't really make all that much of a difference. Sometimes one performs better, sometimes the other. It doesn't really make that much of a difference. It's much more informative than just in-sample fit because of this penalty term for complexity, which makes sure that you don't overfit too badly. You can still overfit with information criteria, but it's much harder, and you have a built-in break that stops you from being too complex for your own good. Problem. There's always problems here. The problem here with information criteria is that you cannot compare them between different model classes. You cannot compare the AIC between an ARIMA model and the AIC for an exponential smoothing model, simply for statistical reasons. There's completely different things. You're comparing apples and oranges, and it's simply you can't do it. It's not meaningful, can't do it. Don't try it. Also, you can't compare ARIMA models with different integration orders. So can only compare ARIMA models with the same integration order on information criteria. So they're limited. They're really limited in application, but better than in-sample fit. Happily enough, there's a third option, and that's almost always available. Selection by holdout performance. How does that work? We again have our forecast, or time series, our historical time series actually. And selection by holdout performance is not so much a selection of forecasts, but more one of methods, forecasting methods. Why? In looking at holdout performance, we use what we call a holdout sample. So we take the last couple of data points, the last couple of observations, 20% of the time series is a rough rule of thumb. So if you have 5 years of data, you hold out the last year. You take the first, say in this case 4 years, fit your model to those 4 years and forecast out into the period that you just held out, that you hid from the model. And then you can assess whether your forecasting method did a good job in forecasting out into this holdout sample. And the advantage is, since we're not looking at in-sample fit, but true out-of-sample performance, we're not overfitting so much. Again, we could overfit, much harder here. And you do that for every single method that you have, whether it's the mean forecast or the ARIMA or your boosting method or whatever else you have. You assess the quality and then pick the method that performed best on this holdout sample. And now you have one winner method that you're going to stick with. Of course, you don't use the method that you just fitted to only the head of the time series. You're going to refit that for the entire forecast, for the entire time series, the entire history, and then you're going to forecast that one out, and you're done. The advantage here is that this is always feasible if you can refit your methods. So even if you're comparing anything else, like boosting, neural networks, whatever, it's a little harder to use this for selection in judgmental forecasts, because it's very hard to say to somebody who is calculating a judgmental forecast, disregard the end of the time series, just look at the beginning. People will always peak. It's hard. You really have to make sure that they don't see what they're forecasting for. You just show them the beginning of the time series if they've never seen the end, and then ask them to judgmentally forecast, and then you can run this experiment, this approach with judgmental forecasts too. But anything that's purely statistical, purely IT, purely in your computer, you can always tell your computer, don't look at this, take the beginning, fit your model, forecast, tell me what you forecasted. I'm going to compare to the actuals that I hid from you. I'm going to tell you how good you were. I'm going to select the one that performs best. This is pretty much the gold standard in forecast selection. So to summarize, there's 3 different main ways of forecast selection. There's in-sample fit. Do not use this. There's information criteria, which are of relevance, but of limited usability, because you can only use them for statistical methods, not for machine learning, or mostly not for machine learning. You can only use them in a limited way to actually compare statistical forecasts. However, third, there's holdout performance, and that is always feasible, or almost always feasible. Now, let's move on to forecast combination. If it's so hard to select among forecasts, perhaps we can just combine them and learn from all of them and not throw information away and just use it all. There's different aspects to look at here. We're going to talk about combination by averaging, combination by pooling. We're also going to talk a little about why does this work at all. And we're also going to talk about something that's been called the forecast combination puzzle in the literature. Onward. Combination by averaging, and that's actually the very simplest way of combining forecasts. We have time series, we have the forecasts from 3 different methods. We're just going to combine them per time bucket. So we're looking at the forecast one step ahead. We have 3 different forecasts from our 3 different methods. Take the average, you're done. All right. It's very simple, and again, it's very understandable and explainable. Can explain that to people with no statistical background at all. And so you get a forecast out that looks like this. It's a little seasonal because 2 of our component forecasts are seasonal, but it's the seasonality in the forecast has been dampened because we're mixing that with a non-seasonal flatline forecast. Can take the arithmetical mean, can take the median, can trim the extreme forecasts, use Winsorized means or anything else. So there's different variations that you have here, but the core idea is really just to take the average of your forecasts. There is also a related concept, which is pooling, for combination by pooling, and that really consists of first removing some forecasts. So if we have a good idea that some forecasts, we simply don't trust them, they're probably not very good, let's just remove them and then average everything else. How do we remove forecasts? Well, here we might, by some analysis, find out that this time series is really seasonal. Then perhaps it doesn't make sense to have a non-seasonal flatline forecast, so we're just going to remove that and just average the seasonal forecasts. We could also say something like, we look at the holdout performance of all forecasts and remove all forecasts that the 5 forecasting methods, or in this case, the one that performs worst on the holdout sample. Or we could again look at information criteria. Whatever, there's different ways of dealing with this. In this case, we might want to just select only the bottom 2, the seasonal forecasts, combine them together by averaging, we again get a nice seasonal forecast, and that might perform rather well. Now, why does this work? Why can't we just select the best forecasting method? Why does it make sense to look at all of them? Why does this actually very often outperform model selection? That's an empirical fact. Very often works better than selection. Why is that? The point is that usually we do not have the data generating process that we just have to find. It's not a question of finding the process that generated our data. Reality is complex, reality is noisy, reality has nonlinearities and influencing factors that we have never dreamt of and whatever. So usually there is no method somewhere out there in the Platonic ether that generated our data, and our job is now to find that, model that, to find that statistical process that generated our data and project that out. No. Typically, our job is to find something that is usually wrong, usually not the data generating process, but that is useful. There's this famous quote by George Box, all models are wrong, but some are useful. We have to find the most useful one. And combination works by reducing the effect of a very wrong model slipping through a selection step. If we select, then we always have a good chance of selecting just by random noise, selecting a model that simply does not do a good job at forecasting. And averaging essentially averages out these possibilities for failure and makes our forecasts more stable and less variable. So you also have something that statisticians like to call the bias-variance trade-off that comes into this here. All right, finally, there is something we like to call the forecast combination puzzle. That's actually a term that's been used in scientific work. What does this refer to? Well, now we just averaged forecasts and just did an arithmetical mean or something. If you think about it, we could also think about doing a weighted combination. Some of these forecasts are going to perform better and some are going to perform worse. Let's give those that perform better a higher weight than the others. For instance, you can look at information criteria. You can again look at Holdout performance. It's always the same idea. And just figure out which ones are better, which ones are worse, and give the better ones a higher weight than the worse ones, and then use a weighted average. And the empirical observation is that unweighted combinations very often outperform clever schemes for setting weights. Optimal weights. Most people claim to find optimal weights in some way. Very often they find that it's very hard to beat the unweighted combination, and that's what people call the forecast combination puzzle. Why is it that unweighted combination very often works better than finding optimal weights? One approach, one possible solution for this has been suggested by a 2016 paper that I like very much, which points to the fact that if we want to optimize weights, then we have an uncertainty in these weights. And these weights have a variance. These weights depend on the data. And this noise in selecting weights and picking the right weights or optimizing those weights, this noise directly goes through to our forecasts and makes our forecasts more wiggly and more variable. And variability is usually statistically not a good thing. We like to remove variability because it's unpredictable. It makes things harder. And in this case, this variance in the estimation of weights may lead to worse forecasts at the end of the line. So bottom line, you may, even if forecast combination with weights sounds like a good idea in theory, in practice it may not work. I'm not saying not to look at it. By no means. Do look at weights. Just be open to the possibility that an unweighted combination or a pooling, for instance, if you just remove the very worst forecasts, that might outperform optimizing the weights. All right, to conclude, if you have multiple forecasts, and who doesn't, we're drowning in a plethora of forecasts because there are so many people who will give their forecasts. If you have a multiple forecasts for the same point in time, you need to figure out a single forecast to deal with, to work on, to decide upon. You can select your forecasts by in-sample fit. No, you shouldn't do that. I'm repeating myself, don't use in-sample fit as a forecast selection criterion. You could use information criteria, or what is probably the gold standard is Holdout performance. However, you can also look at forecast combination, and that just empirically, it's just an observation, very often outperforms selection. So do think about combination. You can do a simple combination by averaging. You can do a simple combination by pooling, by removing some forecasts. It works for, well, reasonable reasons, let's call it that. And finally, very often, surprisingly often, an unweighted combination will outperform setting optimal weights. So do think about not optimizing weights and just going with an unweighted combination. Thank you very much.